Assalamualaikum warahmatullahi taala wabarakatuh. Okay, so first of all, my name is Muhammad Hazmi bin Halim, and my material number is DE200-105. Okay, so in this video presentation, our group will present about our assignment project, which is the high voltage engineering BEV40403. Okay, so this is our video presentation about the electric field distribution on 132 kilovolt polymeric material stem sheet. Okay, so next we will go to the next part. Okay, so the next part is the organization chart, which is I am Muhammad Azmi as the President and Chief Executive Officer of the organization Power Plus SDN PhD, followed by Hafizuddin as the Chief Project Officer, Muhammad Aiman as the Chief Operating Officer, Haziq Nur Hakim as the Architect of our organization, and lastly is Muhammad Waliuddin as a technician of our organization. So that's for organization chart.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Haziq Nur Hakim bin Sarudin. My matrix number is DE2092. Okay, I will go to introduction. Okay, high voltage engineering involves planning, testing, and operating high voltage electrical devices, as well as devising insulation coordination. This project involves designing an overhead line insulator prototype from polymeric material 132 kV, which is an excellent insulation material due to its compact and light size, anti-pollution performance, aging resistance, and anti-pollution capabilities. All the details done by the designer are done carefully to avoid any malfunction when the prototype design is made. COMSOL developed multi-physics software used by engineers and research to simulate real-world designs, devices, and processes across industries. The advantages of employing polymeric as an insulation material are that it is compact and light in size. Furthermore, outstanding anti-pollution performance and suitability for extremely contaminated environment. It also has excellent aging resistance and anti-pollution capabilities. Okay, for the next part is objective. Okay, our first objective to design overhead line insulators using polymeric material 132 kV. Next, to develop a prototype insulator capable of producing high efficiency in the high voltage sector. And lastly, to analyze the efficiency of insulator that has been designed and installed on the transmission line. Okay, next I will explain about our scope of this project. First, material selection. Evaluate existing polymeric material used in the construction of 132 kV electrical equipment within the same shaft. Electrical insulation. Evaluate the electrical insulation performance of the polymeric materials. Next, mechanical strength. Determine if the material can withstand the mechanical stresses and vibration. Next, environmental consideration. Analyze the suitability of the polymeric material for a specific environmental condition within the same shed. Next, comparative analysis. Assess the advantage and limitation of each material. Lastly, recommendation. Potential mitigation measures to address challenge related to the industrial pollution environment. Okay, for the outcome of the work, first, able to design a prototype overhead line insulator by using COMSOL software. Next, able to develop a prototype insulator capable of achieving high levels of productivity in the high voltage sector. Next, able to examine the insulator's effectiveness on the transmission line. Okay, that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Waliuddin bin Ahmad Shukri. My matrix number is DE2086. Now I'm going to present for technical summary. So for the material selection, polymeric materials like silicon rubber and EPDM are used for 132 kilovolt insulation due to their strong electrical insulating capabilities and resistance to weathering, UV radiation and other environmental variables. The core is made to provide strength and support mechanically, and the fitting design is essential for properly attaching the insulator to the tower and conductor. Next, electrical characteristic. Surface resistivity, dielectric loss, and dielectric constant are all important factors in selecting a good insulator for 132 kV insulation system. Polymeric materials with low dielectric constants are often employed in 132 kV insulation system. Next, for mechanical characteristic, polymeric materials used in 132 kV application typically have a low creep rate, which ensures their long-term mechanical stability. And the last one is sheet design. The design of the sheet affects the performance of the insulator. So next, for the technical analysis. First one is the electric strength. The material should have a high dielectric strength to withstand the electrical stress present at 132 kV without experiencing breakdown. Second, thermal stability. Good thermal stability is necessary for the material to withstand elevated temperature caused by electrical stress and environmental factors. For 3, mechanical strength. Sufficient mechanical strength is required to withstand mechanical stress during installation, operation, and environmental factors without compromising installation performance. And the last one, for chemical resistance. The material should have excellent chemical resistance to withstand exposure to moisture, contaminants, and chemicals present in the same shade environment. That's all for me, thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aiman bin Muhammad Rafi'i, matrix number DE200048. Okay, now we're going to the next part, which is part of block diagram. There are consists of 6 block diagram, which is the first one is to create detailed 3D model of the insulator using appropriate CAD software. First thing first, we need to specify the dimensions, material properties, and geometry details. Then we're going to the second block, which is mesh generations. We divided insulator model into the finite number of small elements to create mesh. Then element type and mesh density depends on complexity of geometry and accuracy. Then the third block is material properties, which is to determine mechanical properties of polymeric material. Then properties include elastic modules, density, yield strength, and failure criteria. And last one, material data for manufacture, research paper, and industry standard. For the fourth block diagram, apply boundary conditions, which is define constraint and loads that represent operating conditions of insulator. For the block FEA simulation, we using suitable FEA software to solve mechanical equation for boundary conditions and material properties. And the last block diagram, which is post-processing, which is analyze result obtained from FEA simulation and compare the result with design criteria and relevant standard. And then we go into the part of flowchart, which is the process of our simulations, which is we start by modeling wizard, followed by insert parameter and geometry sequence, then build material, core road, weather shade, and air. Then electrostatic consists of metal fitting line end and metal fitting ground end, and the result we produce without grinding rings. For the second part, which is will produce result grading rings, first thing first, we must insert geometry, which is circle 2 and circle 3, followed by electrostatic grading rings line end and grading rings ground end. Then the result we produce, which is result grinding rings. We're going to the third part, which is to define sunshade. Then after we define the parameters, they will produce the result. And for the last part, which is by first thing first, is modeling wizard and insert the geometry. And the prototype will show on the COMSOL simulation software. I think that's all for me. Thank you.
My name is Muhammad Hafizuddin Cekso, DE200106, and I will explain for the simulation part for prototype polymer insulator. So the first step is to set the parameters value. So this is the value for the
prototype. This value is for the grading ring, and this is for overvoltage amplitude, which is 500 kilovolt, and for thickness of grading ring is 30 mm, and diameter for grading ring is 350 mm, and for the distance grading ring from the end, which is 150 mm. Next, we can construct the design for the prototype. So this is the prototype for the polymer insulator 132 kilovolt. The first step is to design the prototype at the geometry. For without grading ring, we construct until circle C1. This circle C1 is for air, and for circle 2 and circle 3 is for the grading ring. Next is we can insert the material. The first is core rod. Core rod is set to 5 value, which is metal. So this is for the core rod. And for the welder shade, we set to 3 for silicone rubber. This welder shade, and for air is 1. So for the design, we use 2D asymmetric. Then for the this study, we use electrostatic and add metal fitting line end here. We use the value of voltage amplitude, which is VI, and for the metal fitting ground end, here is we set to 0. The same as grading ring at line end, we set the value for VI, and for ground end we use 0 value. Then for study 1 is without grading ring, and study 2 is grading ring. So to see the result, first is electric potential for 2D design. So this is the electric potential for 2D design. We can see that the highest electric potential is at the metal fitting at line end, and we can see at the ground end, which is the lowest electric potential. So this is the 3D design for electric potential without grading ring. And for the grading ring, we can see that the highest electric potential is at the grading ring, line end, and metal fitting line end. And we can see the voltage decrease as the distance between the grading ring increase, and we can see at the ground end is the lowest. So for the tangential electric field, we can compare for the for this simulation, we use first seed shed from the this first seed shed, and the result is we can see that for without grading ring, it increase and decrease dramatically, and for the with grading ring, we can see its stability. So next is for the pollution. So for the electric field norm, for electric field norm without grading ring, we can see that the electric field is highest outer the metal fitting at ground end and line end, only here. And for with grading ring, you can see that the highest electric field norm is outer the metal fitting and outer the grading ring. And for this is for air dry. and this also for air dry, and this is for salty condition. You can see that the electric field norm is higher outer the metal fitting and grounding ring, and at the tips of the weather shade you can see the red color here is the highest. So that's all for the simulation.
So for the conclusion, I will present with the conclusion. So as a for conclusion, polymer insulators are a type of insulator used in transmission and distribution power lines and substations. This group assignment project involved designing overhead line insulator using polymeric material 132 kV stem sheet and developing a prototype insulator capable of producing high efficiency in the high voltage sector. The insulators are composed of polymeric material with various benefits over traditional porcelain insulator, while the rod-shaped insulators are composed of high-strength composite materials with good electrical insulation capabilities and mechanical strength. The group proposed a suitable high-voltage test to improve power transmission system efficiency and reliability while requiring less overall system maintenance. Okay, so for the future work recommendation, as a recommendation, to explore and develop more sophisticated material models to accurately capture the behavior of complex material such as composite or polymers under various loading and environmental conditions. This could involve incorporating nonlinear material behavior, waste or elasticity, and damage models into the FEA simulations. Okay, that's all from our group. Thank you.